Hello and welcome to a new derivatives module. Today, we will be revisiting the process of finding maxima and minima and solving optimization exercises. You should have a good grasp of the derivatives of elementary functions, and although it may not be explicitly mentioned, a solid foundation in basic mathematical operations is also required. To start with, let's begin by revisiting the process of using the second derivative test to determine the relative extrema of a function. In the first step, we calculate the derivative of the function, denoted as f prime of x. The second step involves solving the equation f prime of x equals 0. This means we take the derivative calculated in the first step, set it equal to 0, and solve for x. The solutions to this equation, along with the points where the derivative is undefined, are known as the critical points of f of x. It's crucial to consider both types of critical points. Once you have derived the equation equal to 0, don't forget to check the function and its derivative to know in which points the derivative is not defined, because those are also critical points of the function. The third step, we calculate the second derivative using the second derivative criterion. We substitute the critical points obtained in step 2 into the second derivative. For each of these points, we replace x with the corresponding value, resulting in 3 possible outcomes. If the second derivative at the critical point is positive, the function achieves a relative minimum at that point, denoted as x equal to a. The value of this minimum is the same as the value of the original function without derivatives at point a. Conversely, if the second derivative at the critical point is negative, the function reaches a relative maximum. The value of this relative maximum is f of a, meaning you take the critical value, substitute it into the original function, and that will be the relative maximum value of the function. What occurs if the second derivative is equal to 0? In such cases, we apply the first derivative criterion to determine if it corresponds to a relative maximum or a relative minimum. Let's see this with an example. We're going to determine relative maxima and minima for the function 3x to the power of 4 minus 6x squared. We'll start by finding the derivative of the function. When we differentiate a polynomial, we simply decrease the exponent by 1 and multiply by the original coefficient. So for the first part, the derivative is 12x cubed. For the second part, which is minus 6x squared, we follow the same process. The exponent reduces by 1, and when we multiply by minus 6, we get minus 12x. Once we simplify, we have 12x cubed minus 12x. Can we identify a common factor in this expression? Certainly. You can identify a shared factor in both terms. The common factor for the coefficients is 12 and x in both terms. So you'll have 12x multiplied by x squared minus 1. When you perform the multiplication, you'll obtain the same result. 12x multiplied by x squared equals 12x cubed, and 12x multiplied by minus 1 results in minus 12x. It's essential to verify for common factors. Moving on to the second step, we set the derivative equal to 0 and solve. We take this derivative and equate it to 0. What do we obtain? Let's break it down. Firstly, the constant 12, which multiplies, moves to the other side by dividing. 0 be divided by any number is always 0. What remains is x multiplied by x squared minus 1. I've got 2 terms multiplied that gives 0. When 2 terms multiply together to result in 0, it implies that one of the terms must be equal to 0. It's impossible to find 2 non-zero numbers that, when multiplied, yield 0. Therefore, we can conclude that either x is equal to 0, or the first term, x squared minus 1, is equal to 0. However, I assume you are aware of how to solve for x squared minus 1 equal to 0. The minus 1 is moved to the other side by adding, and we're left with x squared equals 1. Taking the square root of both sides, we have x equals plus or minus the square root of 1. It's important to pay attention to the plus or minus sign. So in total, we have found 3 critical points. These are 0, minus 1, and 1. To determine whether these points are maximums or minimums, we need to examine the second derivative. I've calculated the second derivative here using the product rule, but you could have done it directly with the original polynomial that we obtained earlier. This method is a bit more detailed, but not overly complex. The product rule states that it's the derivative of the first term, which is 12, multiplied by the second term without its derivative, which is x squared minus 1. Plus the first one without derivative, as you can see, times the derivative of the second one. The derivative of the second one, x squared minus 1, is 2x. I already have this expression. I multiplied and simplified the expression to get the following result, 36x squared minus 12. What do we do now? We substitute each of these critical values into the second derivative. When we substitute 0 into the second derivative, we get minus 12. Since minus 12 is negative, according to the second derivative criterion, the function reaches a relative maximum at x equal to 0. The value of this maximum can be found by substituting x equal to 0 into the original function. 3x to the fourth power minus 6x squared. When x equals 0, the value is 3 times 0 to the fourth power minus 6 times 0 squared, which equals 0. The second derivative at minus 1 is calculated by substituting minus 1 into the second derivative expression, 36x squared minus 12. When x equals minus 1, it results in 36 times 1 minus 12, which simplifies to 24. According to the criterion, if the second derivative at a critical point is positive, the function reaches a relative minimum at that point. So, the function has a relative minimum at x equal to minus 1. Substituting x equal to minus 1 into the original function, we get minus 3. Now let's determine the value of the second derivative at x equal to 1. When we substitute, we obtain a positive value of 24. This implies that the function reaches a relative minimum at x equal to 1. What is the value of this minimum? We take the original function, substitute x with 1, and obtain a value of minus 3. Graphically, we have this situation. The function has a relative minimum at minus 1, a relative minimum at 1, and at 0 it had a relative maximum, as we calculated a moment ago. I hope this review on calculating relative extrema and fundamental derivatives was helpful. Reach out if you have more questions. Until next time.